Yes, so Srikal students, so let's start properties of bulk matter, especially properties of solids, and let's study what is stress and strain. Well, whenever a body is applied with some external forces, the body may be spherical in shape or the body may be like a bar. We may apply external forces, tensile force or compressive force. There is an internal mechanism in the body which tries to resist the change in the dimensions of the body. Those internal resistive forces per unit area, the area on which the resistive forces exert, that is known as stress. Well, the magnitude of resistive forces is equal to the applied force. The unit of stress would be Newton per meter square, just like the unit of pressure, that is Pascal. So, in simple words, we can say stress is restoring forces per unit area. Now, what are the types of stresses? So, first we have normal stress. It all depends upon how the external forces are being applied. Students, let's say we are having a bar and we have been applied the tensile force. Tensile force is a force which tries to elongate a body, means which tries to change the original length to L dash, where delta L, that is change in length, is equal to L dash minus L. So, under the effect of tensile force, which is being applied on this area of the body, right? So, now the force applied F divided by this area. This is the area on which the force is being applied, is the normal stress. In the case of tensile force, when delta L is positive, the change in length, we will say the normal stress is tensile stress. Tensile stress comes into play when the forces which are being applied on the body are tensile in nature. That means they try to elongate the body, try to increase the length of the body. But in the reverse, in case I apply this force, I try to compress the body. When I try to compress the body, well, my line looks little inclined to this surface, but actually this force is perpendicular to the surface. Very important. If the forces are perpendicular to the surface applied, then only the stresses produced are known as normal stresses. So now F dash is a compressive force, and under the effect of compressive force, the internal resistive forces set up in the body per unit area are known as, the stresses induced in the body are known as compressive stress. Well, in case of compressive stress, delta L will be negative. The If this is the length of the body. This is the compressive force applied on this area, right? Let's say compressive forces are applied on this area. Then the final length of the body I'm showing with red color. The body might get compressed by some length. So in that case, the final length of the body, L dash minus initial length, would be negative, indicating that compressive stresses are being induced. So normal stresses are of two types: tensile stress and compressive stress. Let's go further. There's another type of stress other than normal stress, which is known as hydraulic stress.
So this means that tensile strength and compressive stresses are perpendicular to the surface.
To the surface. Very right. Only when, let's say, this is the surface, right? This surface is A, and the forces applied are like this. And these forces are trying to either decrease the length of the body. Well, these compressive forces applied perpendicular to the side by areas would try to decrease the length of the body, giving rise to compressive stresses, which are also falling under the category of normal stress. And in case this force is reverse, now the body is trying to elongate laterally, and then the stresses induced will be known as, yes, would be known as tensile stresses. Well, both these stresses, compressive stress as well as tensile stress, are applied longitudinally along the length.
So in case of tensile stress, the L delta L will be positive.
100% right. This is the body. When you apply tensile force, you're trying to stretch the body, you're trying to elongate the body. So, final length of the body will be this, it will elongate. This is L dash, original length was L, L dash, final length minus original length, that is delta L. As you can see, in this case is positive in case of tensile stresses. But only thing you have to remember, that tensile stress is a stress only when the forces are applied perpendicular to the area. All right. Now let's say, students, we go for hydraulic stresses. Hydraulic stress here, in case of longitudinal stresses, that is either tensile stress or compressive stress. We were concerned with the change in the length, right? Either decrease in the length or increase in the length. We were not really considering other phases. But hydraulic stress comes into picture, especially when, let's see, this is a container, it has liquid under high pressure. Now, this liquid under high pressure is there, and what we do, we put a body, let's say the body is like this. The body is like this. So, what's happening? See, students, now there are external forces acting on the body from all the directions, but all the external forces which are acting on the body, if you draw the tangent at which a particular force is being applied by the fluid, this force will be perpendicular to the tangent. So, under the effect of these external forces, the external forces are also known as deforming forces because they try to deform the body. The internal mechanism of the body is set up how internal mechanism of the body is set up. So there are forces which try to oppose these forces internally. Now these forces, these internal forces acting along the area. Now it's whole area of the sphere, 4 pi r square. So this internal resistive forces acting from inside to outside is, is account for hydraulic stress. So now hydraulic stress is defined as again the restoring forces per unit area. Now one important point to note here, in case of hydraulic stresses, the solid body undergoes a change in the volume. If V is the original volume, V dash would be the final volume. So delta V would be V dash minus V. Am I right? So hydraulic stresses are induced in the body when there are external forces acting on the body at every point on the external surface of the body. And internal resistive forces per unit area are known as hydraulic stresses. In case of hydraulic stress, once again, there's no change in the geometrical shape on the body. The sphere remains the sphere. As it was the last case, the bar we had taken in case of normal stress was cuboid, and under the effect of the normal stresses or deforming forces, it remained cuboid, but the length changed. So in this case, the diameter is changing, but the body geometric shape remains the same. Let's go further. Now we have another type of stress that is known as tangential stress. This is also known as shearing stress. Well, when does this comes into play? Students, it comes into play if this is your book, right? And what do? You somehow try to apply the force on the upper cover on the book. So the upper cover comes like this. Some pages of the book, including the upper cover, tries to slide over the bottom pages of the book, right? So there comes shearing stress. So in order to understand it better, let's say we have a cube or a cuboid. Now let's say the bottom surface of this cube is fixed. Very important. In engineering, we show it like this. This means bottom surface is fixed, or you simply write it down. It's fixed surface. When the bottom surface is fixed, where do you apply the force? This surface is not going anywhere because this is fixed. You apply force on the top surface, either in this direction or in this direction. Let's say we apply force left to right. So what happens? This surface will try to slide over. It will try to slide a little bit towards the right side, right? So it's not so strong, imagine. It's not an iron box. Maybe you could say it's a it's a strong rubber cuboid, or simply heap of paper, all having same size, maybe deck of cards. So what do? You are applying force on the top surface. Now what will happen? This point will shift to this point, right? This point will shift to this point. Similarly, here, this point will shift to this point. So this red would be the new shape of the body. Am I right? So now you could say the upper surface of the body on which the force is applied. Upper surface of the body shears, or you can say upper surface of the body slides towards the right side a bit. So now there's no net change in the volume of the body, as it was the case in case of hydraulic stress. The volume changed to V dash. But in this particular case, in tangential or shearing stress, the volume is remaining same. Am I right? So, but the configuration of the body is little bit changing. So now tangential or shearing stresses are induced in the body, and this tangential stress or the shearing stress is equal to magnitude of force applied divided by magnitude of area of cross section. Magnitude of area of, as you can clearly see, students, in this case, unlike normal stresses, the surface on which the force is applied, the forces are not acting perpendicular to the surface, as it was the case in case of normal stresses, whether tensile stress or compressive stress. In both the cases, the deforming forces or the applied forces were always perpendicular to the surface. Not in this case. This is the upper surface. On this surface, you could say, the forces are being applied, right, on the top surface. So top surface slides. So you could say the shearing effect across the whole height of the body. So this is the new shape of the body, but the volume is remaining same. All right, students. Having done with this, we would come to this figure just now, very soon, when we calculate and actually define how we can calculate the tangential stress. Tangential stress is very easy to observe. Suppose you have deck of cards, right? And then you try to give a little hit to the top card, and then you see this is the new shape of the cards. Total volume remains same. So you could say every card has sheared with respect to the card beneath it, so that there are shearing forces and shearing stresses induced in that deck of the card, right? So guys, now let's discuss what is strain. Whenever a stress is applied, there are strains in the body. What is this strain? Students, under the effect of every deforming force is same as applied force. Students, any doubt like this girl is asking? You are most welcome to ask doubts. I would be happy to answer it, and then that will open more concepts. Under the effect of deforming or applied force F, there is a change in configuration of the body, always. Now we say the body is strained, or you can say the body is deformed. In all the cases of stress is applied, we have discussed so far. Now, the ratio of change in configuration to the original configuration is what is known as strain. What about units of strain? Let's say the configuration is changing in terms of length, as it was the case in, let's say, tensile forces. Tensile forces F are acting on this bar. So the length of the bar changed by delta L, which was positive. So students, change in configuration in this case, not the changed configuration. It is change in configuration. Well, that was delta L divided by the original configuration. Original configuration was L, is known as strain. So what will be unit of strain? Change in configuration may be in mm, original length also in mm. So some foreign books define unit of strain as mm by mm. But then even if you say it is dimensionless, that's fine. Its dimensions are m0, l0, t0 in terms of basic dimensions. Now, students, what are the types of strains? Particular stress gives rise to particular strain in the body. So the first type is longitudinal strains. Longitudinal strain. See guys, this comes into play under the effect of longitudinal stresses or normal stresses. Deforming force produces a change in length alone if deforming force or applied force produces a change in length alone, only in length. The strain produced in the body is known as longitudinal strain. Sorry, I wrote it stress. I should have written strain. So, longitudinal strain would be equal to change in L divided by original length L. Number two. So, before stating second one, you see students, both tensile stress and compressive stress both will give longitudinal strain, right? Number two comes, yes students, now we have hydraulic stresses. Hydraulic stress gives rise to volumetric strain. So you remember the ball dipped in high pressurized fluid. Its geometry remained same, but its volume decreased, right? So there we have volumetric strain. If deforming force produces a change in volume alone, as it was the case in hydraulic stress, the strain produced is known as volumetric strain. So students, volumetric strain would be equal to change in volume, that is delta V divided by, yes girls, anyone?
V.
Beautiful. This was original volume. not V dash. V. Remember, V changed to V dash. But in the numerator, we don't take V dash. In the numerator, we don't take L dash. We take original length. Delta L with respect to original length. Right. And now we have third type of strain, students, that is shearing strain. So obviously, when the body is strained or deformed under shearing stress, the strain produced will be, yes students, shearing strain. Now we want to define this. So let's get back to the previous slide. So see students, here on the top surface, we had applied the force F. As a result of this, this top surface moved little bit towards the right side, right? As in this case of deck of cards. So this surface, right? This surface has been, you know, this is angle theta. This surface has been inclined by angle theta. That is also the case here also is theta. So now students, here, this is the deflection in the surface, you can say, by the length delta L. What is delta L? Now I'm taking longitudinal distance towards x-axis. See, this is delta L. This surface was originally here, and now this surface is here. So I say this is delta L. Now students, I'm going to magnify this right angle triangle. See, it's like this, then it's like this and this. Am I right? So this is 90 degree. So this is theta. Can you tell me what is tan theta? Use your trigonometric knowledge. What is tan theta in this case? This length is delta L. This length is delta L. So what will be tan theta? Come on. Let's say this length is L. This length is
Tan theta is delta L by L.
tan theta is delta L by L. You must remember L was this distance. Very, very important. This was L, or you name it by capital L, doesn't really matter. So tan theta is delta L by L. Now students, the knowledge of trigonometry also tells you, you can see trigonometric table, when theta is small, tan theta is always equal to theta. Is it true? Yes. When theta is 0 degree, can you tell me, Ishma, what is tan 0? When theta is 0 degree,
0.
tan theta is 0. Perfectly right. That proves that when theta is small, theta is equal to tan theta. Theta, I think, should not be taken in this degree, but in radians. So tan theta is equal to tan theta, because I've been telling you that mistakenly I've taken 0 degree. Theta must be taken in radians. Whenever you want to use angle for calculation purpose, take in radian. So we can say tan theta is equal to theta is your shearing strain. This is your shearing strain. And yes, Ishma, this is equal to delta L. What is delta L? Delta L is exactly this surface, this point A. If this point is A, it moved to A dash under the effect of shearing force. So this A dash distance is delta L. Delta L divided by L is the shearing strain. So as stated before, it also has no unit. All right, students. With this, let's do Hooke's law also. So now we have got an idea that stress and strain are related, brother and sister. So we have stress, there is corresponding strain. We have longitudinal stress or normal stress. They give rise to longitudinal strain. Am I right? Yes, Ishma. If I have hydraulic stress, it gives rise to what kind of strain? Hydraulic stress gives rise to
Volumetric.
volumetric strain. That's beautiful. Similarly, I have also seen that tangential stresses or shearing stress gives rise to shearing strain, that is theta, which is equal to delta L by L. All right, this was the surface. It changed to this under the effect of the shearing force. This is delta L by this length L is exactly tan theta. Theta is small because you see rigid bodies will not show more delta L. They would slightly, the edge would slightly get deflected. So delta is always small. That's why we always say theta is equal to delta L by L. So what is Hooke's law, guys? Hooke's law states that stress is directly proportional to strain. Always? Not always. Under some limit, the stress is proportional to strain. So guys, if we draw the graph, you see here we should take the parameter which is in your hand. I'm telling you a hidden truth, which you are doing, and then the effect you should plot along y-axis. You know, so here is stress in your hand or load applied in your hand, Ishma. What can you change?
So where
Let's say you have a ball in your hand. You're pressing the ball. So is stress produced in your hand or the load applied is in your hand? What is there? What can you change?
load.
Beautiful. So load. I told you the when you talk about different subjects, the terminologies also change. So many terms in chemistry means different. In thermodynamics, they mean different. Work, heat transfer has different meaning in thermodynamics, has totally different meaning in physics. So here our force is changed to load. Load applied is in x-axis, right? Maybe in newtons. And then extension. What is extension? Extension will tell you the strain because we know strain is extension delta L by L. So this extension will tell you what is strain. So if you apply this, it's interesting. It will be a straight line graph. Knowledge of mathematics tells us that straight line graph is linear. Linear means directly proportional. So this is experimental validation of Hooke's law that till a limit, till some limit, what is that limit? That is known as Hooke's limit. What is so special about that limit? It is also known as elastic limit. There's a limit till which the applied load, that means now this load will help you to calculate stress. How? Load divided by area is stress. So from load you will get stress. From extension you will get what, Ishma? Strain. So this straight line tells you that stress is directly proportional to strain till Hooke's limit or till elastic limit. So in other words, we can say the stress by strain is a constant, and that constant E is known as coefficient of elasticity, or is known as of modulus of elasticity. Modulus of elasticity or coefficient of elasticity. Thank you very much, students. That's all with this lecture. Do revise it. See you tomorrow with the third lecture. Have a nice time.